All right, here we go. Physics reaction video number 40. Can you believe it? 40. I'm amazed. I'm actually going to put myself over here. Looks like I can always fit there. That's pretty cool. Did a search for honors physics. That was it. I filtered for this month. So let's see what we can do here.
All right, we're going to take a look at momentum and impulse today. The equations that you're going to use are momentum. Momentum is represented by little p. It's mass times velocity. Mass being a scalar, velocity being a vector.
So right away, like, hey, we're going to do this stuff. We're going to be working with these things. We have this crazy, stupid choice of P for momentum. There's no letter P in the word momentum. Maybe we should call it momentum. And really loved that. It looks like maybe that's written in bold. I can't quite tell. But hey, mass is a scalar, velocity is a vector, makes momentum a vector. That's super interesting and useful. I can't quite read what it says at the very top here. I don't know if this is a review or if this is their homework. Kind of looks like some fill in the blanks here. So I'm not sure if this is going to be enough space. But I do like, using the same structures that the students have, because, it saves a tiny little step of, I'm working on problem number 3 now or whatever, because they can literally see it. So that's pretty cool. Just go back a little bit.
Velocity, mass being a scalar, velocity being a vector. We're also going to take a look at impulse. Impulse momentum theory is very similar to work energy theory or theorem. And the impulse is your force times your change in time is equal to your change in momentum. Right, and our change in anything is going to be our final of that thing minus our initial of that thing.
So note that there's no subscripts on the mass. So I've talked about this a lot, right? That in principle, the mass could change, but we're always going to start with problems that sort of make sense to students, like throwing a ball against a wall or 2 balls whacking into each other, as opposed to like 2 bits of putty, like swapping a little bit of putty, right? That's harder to do. Certainly, I constantly am thinking about eventually like nuclear physics, where mass is like the whole story. Change of mass is the whole story when it comes to nuclear stuff. So I'm always curious about what that transition is like for students, because they've seen so much of exactly what she's doing here, which I love, of course, because, look, there's so much of their lives where this basically applies. And of course, in nuclear, it's even worse, right? Where mass literally like disappears, right? It's one thing for like, a little block to be shifted over to another cart or something where the total mass stays the same, but it's another where like the mass literally changes and becomes energy. All right, so cool. She said something very fascinating, and I'm always intrigued by this. She said that the impulse momentum theorem is a lot like the work energy theorem. To me, it's so interesting that so often we teach the work energy theorem first, because to me, momentum is king, right? So momentum is the whole story. Energy is this made-up thing that physicists made up to help us do accounting, right? Literally, just to do some accounting of all of these momentum swaps that are constantly happening. And so the F over time versus F over space. So we're doing F over time versus F over space. So imagine, what I have my students think about is like a region, a force field region, whereas when something enters it, it feels a force, maybe pushing in this direction. So as it goes through, it feels that force and it gets through. So if it's a fixed distance, I don't care how fast you're going through it, you're going to get the same energy bump, right? But if it's a fixed distance, the speed you go determines how long you're in there. So that means your momentum change is dependent upon how fast you're going. So there's actually big differences in sort of the impact of these things. But yeah, their structure is so similar. Like, hey, let's figure out how long this thing felt a force. Well, what do you mean by how long? Do you mean how far? Or do you mean how long? Right? And so there's huge similarities between the two. I love that. Impulse is a vector, and of course, energy is not. So there's a big difference there. So I guess this one is harder because it could be multi-directional. Just go back a little bit.
Change in anything is going to be our final of that thing minus our initial of that thing. The units for momentum being a new variable we're working with is kilogram meters per second.
Why don't we
The
name
units for
that?
impulse are going to be Newton seconds, right? Force times time, or kilogram meters per second.
Because, of course, those two have to be the same
Let's take a look
of
at
that.
number 1.
Another sheet of paper.
What
Okay.
happens to our momentum if we have twice the mass and the same speed? So if my original momentum was 24, I will do it like we did before. 1 times 1 is 1. So originally, we look at a base equation, and then if we have twice the mass, keeping the same velocity, we're essentially doubling our momentum. So if we started with
Okay, man, this is so cool. At first, I wasn't sure what she was doing. I was thinking maybe like she was building every structure is always going to be 1 times 1 equals 1, and then you slowly like increase. You put in the amount of each one and see how the result changes. But I actually think that this is a structure she uses when doing comparison type problems. So she's saying the original we'll call 1. And then we'll look to see where changes happen. Well, hey, look, this 1 becomes a 2. Nothing else changes on the left-hand side. So the result becomes a 2. That's a super cool way of doing that. I think about saying to my students all the time as follow-up questions, what would happen if the mass doubles? And what I've noticed is that for the students who do it algebraically, right, they have letters all the way to the very last moment when they plug in. Those students, when I ask those questions about what happens if it doubles, they're easy. They look numerator, denominator, where is it at? Answer. Right here, she's saying, let's think about that, but let's just say, let's put in, I guess, numbers, right? These 1s and 2s. I think that's really, really cool. So I believe what momentum, twice the mass. Oh, right, because this problem number 1 has several questions like this. So she's going to do this a lot, I think. Oh, this is really cool. Let's keep going.
With 24, our new momentum is going to be 48.
That's really cool.
The same mass, twice the speed. Same mass, twice the speed.
That's cool.
It's going to have the same effect. We're going to double our momentum. 1/2 the mass. Here, I should say mass times velocity gives us our momentum.
Cool.
And twice the speed. Right, 1/2 times 2 gives me 1. So my
Which means no change. Boy, this is really cool.
And so on. So try the rest on your own.
Ooh. Okay, so just try the rest on your own. I guess this is not a solution set so much as a worksheet, right? So I'm going to do, what does she do? 1, 2, 3 of them, and there's 6 of them. So that's really cool. Do the others get any harder? Same mass, half the speed, 3 times the mass, 1/2 the speed, 3 times. Okay, so these are all going to be pretty straightforward. If you were to do like kinetic energy things like 1/2 mv squared, these problems get a little bit trickier. And I really like the fact that some of these choices have something other than doubling, like 3 times, because the number 2, it's because 2, right? We double things a lot, we cut things in half a lot, and yet when you square a 2, it just feels like you've doubled it, right? So I really like mixing in other numbers like 3. Okay, but very cool to model how to do the first few, and then you do the next ones. One of the questions I have for folks is, we do that kind of thing a lot, and sometimes parts D, E, and F really jump up in difficulty, right? So are we doing any favors if we do the easy ones and leave the hard ones for them? In this case, it doesn't seem like D, E, and F are any fundamentally different than A, B, and C. Interestingly, I'm really, really glad she did C, because C is the first one where both of them changed. And so then you can really see, okay, I can handle changes of both ones. So very cool. I'm just going to back up a little bit.
So on. So try the rest on your own. And I'll do a few of these. So according to the Guinness Book of World Records, the fastest baseball pitch was delivered by Nolan Ryan in 1974. The pitch was clocked at 100.
So that's not true anymore. Here, let me just do a quick, ask my phone. Hey, Google, what's the fastest baseball pitch?
The fastest pitch in the world is 105.1 miles per hour by Aroldis Chapman.
105, I believe it said. So this, right, so when you have materials that get dated, you can imagine the baseball playing student saying, "Oh, that's not true," right? Like for someone like me, Nolan Ryan, oh, I would see that. Yeah, Nolan Ryan, what a monster! He was such a great pitcher, right? Because I remember watching Nolan Ryan pitch. But for our students these days, I mean, Nolan Ryan, he's still in the baseball world. He's like a manager or owner or something of the Round Rock something or others. But he's not contemporary. And this is, you heard what Mike Google said, which is that it was 105. That's actually a big difference from 100.9. So my question for you guys is, how do you deal with dated materials, right? My guess is she's just going to plow forward, because from the perspective of what to do here, it's a plug and chug problem, right? But how do we deal with the fact that some students might be turned off by this or be like, what, this can't be right? Or they'll do exactly what I just did, which is ask Google, even though fundamentally there's no difference in sort of the practice we're trying to get them to do with these momentum type problems. I think it's too much to ask. You should vet all your materials and change every single thing. I think that's too much to ask. Instead, I think we need to think about, how might we respond to a student who says, hey, wait a second, I actually don't think that's true. And of course, I don't believe this is an interactive video at all. I don't think there's any students here. So I would love to know if any of her students said, hey, wait a second, there's something funky here.
0.9 miles per hour. We want it in meters per second. So our velocity is going to be 45 meters per second.
And notice what she's doing now, right? So the conversion was done for the students, 45 meters per second. I always mentally do about a factor of 3. I didn't realize it was just a factor of 2. Let me check. Hey, Google, what is 100 miles an hour in meters per second?
100 miles per hour is equivalent to 44.704 meters per second.
I don't know why I always was doing a factor of 3 in my head. That's funny. I wonder where that came from. I mean, easy to check. Should have known. Basically, the ratios that we're talking about are 3,600 seconds in an hour and 1,609 meters in a mile. 36 divided by 16 is the same as 18 divided by 8, which is the same as 9 divided by 4. Yeah, okay, so it's 2.25. So somehow I've always rounded that up to 3. Oh, well. But my point is, it was given. So sometimes students, they hear something that connects to their lives. Oh, 100 miles an hour, that's super cool. And they're like, oh my God, I'm in a physics class. I can't believe they gave me 100 miles an hour. I got to convert it. So nice that somebody just put in parentheses, oh, that's 45 meters per second, so that they can at least get to the calculations faster. I mean, I think some would say, "Ooh, our students should know how to do that. We should purposely give them miles per hour to make them do the conversions." But I think in this case, that's not what she wants them to be practicing. So it's nice that it was given in meters per second as well.
Okay. Determine the impulse required to give this ball with a mass of 0.145 kilograms such this momentum. So my momentum is mass times velocity, right, is also equal to my impulse. Right, change in momentum is equal to my impulse. So this initial momentum of the ball before it gets thrown is going to be 0. So we're really just looking for our mass times our velocity. So in this case, it's going to be 45 times 1.545.
Hey, Google, what's 45 times 0.145?
The answer is 6,525.
Oh,
6.
it didn't get the decimal point.
5.
Look at all those significant figures.
Meters per second, or you could also do in seconds.
Yeah, I love it. So let's talk about that. 6.525 Newton seconds. The picture, right? Maybe a tenth of a second. 1,001, 1,002. This is is half seconds. Dun 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 is a quarter of a second. Dun 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 dun. Quarter of a second. Let's call it quarter of a second. Maybe a tenth of a second. So if it's tenth of a second, that's numbers I can do in my head. That's 65 newtons. So 65 newtons is what it would take to lift a 6.5 kilogram thing, which is about 15 pounds, a bowling ball. So the force to lift a bowling ball, applied for a tenth of a second. That's less than I was thinking. So I'm trying to think, lifting a bowling ball. Double check me. I must have done something wrong there. That seems funky to me. You know what? I think. How long is this? I don't want to go too long today. Yeah, I think I'll bring it to a close there. Some really, really great stuff in this problem, or in this entire video. I think that focusing on what the tools they need to use is really, really cool. I tell you, I just love. I'll back it up so we can see. I loved. Should turn the page over. This stuff here. That was such a cool way to do it. And I could imagine it working in lots and lots of sort of comparison problems. All right. Well, hey, everybody, I hope you have a great day. And remember, physics teachers are awesome.